All right. You got some questions? Let's talk about it. I'm just going to go through in the order that you asked them, and hopefully it's going to help you out. Let's see. All right, number 1. You said, can an earthquake make a mountain? No, an earthquake can't make a mountain. However, when you have a really seismic zone, you might have some stuff going on. And in a mountain building process, you're definitely going to have a lot of earthquakes happen, but it can't make a mountain. 2. How can people determine an earthquake before it happens? Well, we can't really tell an earthquake before it happens, but our GPS sensors and our technology have gotten a lot better that we can start to see movement along a fault, and we can kind of get an idea that when's going to happen, but we still can't predict it. What are the 2 types of seismic waves? Are there any similarities between S waves and P waves? They seem pretty opposite from each other. Well, the 2 different waves are the primary wave, the P wave, the secondary wave, the S wave. The primary is always going to be faster. The secondary is always going to be the slower of the 2. What are the differences? Well, the primary is a longitudinal wave. An S wave is a transverse wave. If you're in first period, ignore that part. They are pretty different. They're the same in that they're both waves and they act like that, but how they act itself and the properties itself and how they move, they're pretty different in that regard. So they're not exactly opposites, but they're not exactly the same either. What are they? There you go. That's what they are. Why should we only use the moment magnitude scale? Why are there multiple scales if really we only need to use just one? Great question. Well, we've gotten a lot better at our math and our geophysics and our modeling and things like that. So before we had the Richter scale, which we thought was the good scale to use, and it was for a long time until we realized that over a magnitude 5.0, the Richter scale actually doesn't do that well. The math gets weird and it doesn't work as accurately as we'd like it to. So geophysicists came up with the moment magnitude scale, which is based pretty much purely on math and actual physics, and it's a lot more accurate, and that's the one we should use, and that's why there's more than just one. Next question. Do we have to remember the different layers, or what the different layers of Earth are made up as? You don't need to memorize it other than remember that the cores are both iron and nickel. The outer core is liquid, the inner core is solid, but other than that, I gave you those reference sheets for a reason. Make sure you know how to read them. Go over magnetic polarity. I'm not sure what it is. All right, magnetic polarity is in the seafloor, and we see that, no pun intended, the ocean's bedrock, that mafic bedrock, that's another question you had on here, spreads out from the mid-Atlantic ridge. Well, we notice that on each side, the polarity, whether it's positive, meaning the iron faces north, or if it's negative, meaning the iron faces south, but that was north at the, did you see where this gets complicated? Basically, what you need to know about magnetic polarity is that we notice that every now and then north flips directions as we go away from the seafloor, or the seafloor center. But it's the exact same thing on both sides, which means that all the seafloor had to come from the same place, which for us is the mid-Atlantic ridge. It's a really confusing concept. All you need to know is it basically proves seafloor spreading. Do we need to know faulting, folding, and tilting? I would look over what they are. Question 2 on the bell ringer. What makes geological hazards so dangerous? They're so dangerous because they're not predictable and they happen very quickly. Most things in geology take forever. Tens, hundreds, millions of years, hundreds of thousands of years, tens of thousands of years. Geological events like earthquakes, landslides, stuff like that happen in seconds. That's what makes them so dangerous, along with the fact that we can't predict them. Where are most shadow zones? So shadow zones aren't anywhere. They are only based on where the earthquake happens. So if you look near the last page of your notes, you'll see that little graph with the shadow zones on it. Those shadow zones are there because of where that earthquake happened. If you rotate the earthquake's position all the way around the Earth, the shadow zones will just always be on the opposite side of the Earth. They're not in any one place. They follow basically straight across the Earth. What's the difference between the Mid-Atlantic Ridge and the Mid-Ocean Ridge? Nothing. Ours is just called the Mid-Atlantic Ridge. What will our continents look like if they keep moving away from each other? Is there a possibility for Pangea to form again due to seafloor spreading? And is there a possibility that a plate could split into 2 or more plates? So those are all great questions. What could happen? Well, eventually all the continents, all the plates are going to run into each other again like Pangea. All those continents are eventually going to be a supercontinent. When? We're not quite sure yet. What's it going to look like? There's 4 leading ideas, and I'm not going to get into them because they're not that complicated, but don't want to, boggle your mind with adding new stuff the day before or the day of, depending on when you watch this. Yeah, it's going to happen again. Could a plate break? Yep, and they will. Plates are all the time being destroyed and recreated anyway. So, I mean, it might not just fracture like an egg, but it's all the time being broken. What's the relationship between volcanoes and earthquakes? We typically see a lot of earthquakes happening before a volcanic eruption. In an area that has a lot of seismic activity, if we start to see these little tremors, these little foreshocks happening, and it's near a volcano, we know that the volcano is probably about to erupt. We also know the volcano might erupt soon if we see the ground start to subside. So if the ground looks like this and it has magma underneath it and all of a sudden it starts to sink and kind of get a depression in it like this, the magma's going somewhere, probably is getting ready to come out of the volcano. What exactly is liquefaction? Well, liquefaction is when you have really fine-grained sediments like muds and silts, and you build something on top of it. You don't have to, but that's why we're talking about it. But the ground shakes so quickly that the water content that's in the ground with the mud and the silt starts to move up towards the surface, and as it's shaking, the ground is no longer solid. It's basically like a liquid. So it's called liquefaction because the ground temporarily basically turns into water. Could you elaborate on a more complex boundary like continental convergent boundary? Sure. So in this example, 2 continental plates converging towards each other. The density is the same. They're made out of the same granite felsic bedrock. So when they hit each other, not going to go underneath. One's not going to subduct because it's the same density. And one can't go on top because that's the same thing just in the other direction. So eventually they're going to hit, keep pushing, and eventually bend upwards. We called it folding. And that's how mountains form. That's how our mountains formed in the Appalachians when North America ran into Africa. How do meteorites help us study Earth's interior? Good question. If you remember back to astronomy, you'll know, or hopefully know, if not, go look it up, that all of the planets came from the same stuff. Like it all came from stuff that was floating around in space. So if we know what is floating around in space and we can still see it in the form of meteorites landing on Earth, then that's what formed the inner parts of our planet. So if we study those, we study what the Earth looked like way before anything showed up onto it when it was still a hot and molten mess. I just have a question. If we have to remember what are the different layers of Earth? Nope. Again, reference sheet. No page 5, no page 10. Be able to use them. Where is the oldest seafloor at? So, the oldest seafloor is going to be near the continents. Why? Well, the new seafloor is made at the Mid-Atlantic Ridge or the Mid-Ocean Ridge, based on that question you just asked. Ours is just called the Mid-Atlantic because it's in the Mid-Atlantic. And it's going to be near the continents because as the new seafloor is made, it goes up in the middle, it pushes itself out, eventually gets to the continents, subducts underneath. So there's another type of boundary, an oceanic continental boundary. You're going to have the floor get pulled underneath, that slab pull, that's going to get pulled back down into the mantle. And remember that the convection currents in the mantle are driven by density. Eventually it's going to make its way back, go up to the seafloor again, be created as new seafloor, but that stuff that's really old has made its way over to the continent and it's about to get pulled underneath. Why did scientists reject Alfred Wegener's idea of continental drift? Because he couldn't explain what I just said. He had pretty much everything right. He had all this information, he had all this data, he had all these ways to make it make sense, but he couldn't explain why the continental plates moved. He didn't know about the convection currents in the mantle and the differences in density and all that stuff. Once we explained that, he was right, but he couldn't, so scientists, rightfully, I might add, didn't accept his idea. Without evidence, science is not going to accept what you think. What would you say is the most important thing we have to know, and why can S waves only travel through solids, and why are they absorbed by liquids? Most important thing to know, I wouldn't say there's any one thing other than remember that density is really important, and it's going to be what's the difference in the layers, and it's going to be what drives the convection currents in the mantle. Density is going to come up again in weather, which is the next unit. Why can S waves only travel through solids? So remember, it's like a rope. So if it's moving like this, and let's say you're trying to do a rope like that across a pool. Well, Can you really make the rope go like that through the pool? No. Once it hit the water, it's going to flatten out and kind of get stuck, right? Well, that energy is going to get into the water and then just kind of dissipate out. It's not really going to make it go through. So why can't S waves make it through the liquid outer core? Well, it hits that liquid outer core and it starts to dissipate. It doesn't make it through. What's the difference between continental and oceanic crust? Oceanic crust is more dense, but it's thinner. It's mafic. Continental crust is less dense, but it's thicker. It's felsic. Continental crust is 2.7 grams per centimeter cubed, and oceanic is 3.0 grams per centimeter cubed. So when they run into each other at those continental oceanic convergent boundaries, the oceanic will always go underneath because it's more dense. What are they made of? Look back in your rock cycle notes if you didn't write it down here, and go back and figure out what they're made of. It's kind of important. Maybe not the most important thing, but kind of important. Those are the 20 questions that you asked me to go through. Those are the ones that you listed, and yes, some of you had duplicates. Some of them I didn't answer because I'll be honest, you're not going to need to know it on a test, so I didn't want to confuse you by answering it. If you asked a question and I didn't answer it, and you still really want to know it, probably not. But if you do, ask me again, ask me in class, send me an email, whatever. Have a good time tomorrow. Hopefully, you'll get a good grade. We'll see. Maybe not. I don't know. Depends on how much you study. But either way, good luck.